So if you have a point outside of a cycloid and you want to be able to bring it in tangent of that cycloid, how do you go about doing that? I thought of a couple things. I was trying to play with circles because I know the tangent is the minimum radius necessary, and that would form a perfect circle. Again, I decided to use a trig solution, and my daughter Roxana, who is just about to finish her civil engineering degree, helped me like piece out the formula and then to go ahead and get it all derivated nice and pretty. So we'll go ahead and run through the program here, and it's really high level. If you want me to break out any of the steps, go ahead and leave me a comment, and I can go ahead and I'll set up a video to do that. We're going to deal with Newton's method, and there's plenty of videos on that. Again, there's plenty of videos on derivation, so it might be even a better idea for you to go do some searching. Michael Beeson, I know he's a professor out in California, and he's just got an incredible amount of videos from everything from mechanics to physics to thermodynamics. You name it, he's got it out there. Go give him a look-see on anything that we couldn't find here. In a previous video, I did determine, again, couldn't find it out on the internet, a simple formula for finding the tangent along a cycloid. And that turned out to be t equals pi minus 2 times alpha. And alpha is the amount of degrees in radians. And t is the distance along the x-axis, where the actual circle is touching the baseline. Okay, that would be the generating circle. So go ahead and watch the presentation. Hope you have fun. Leave me some comments, like, subscribe, whatever, and we'll catch you at the end, or I may just close it out. We'll see. I haven't decided yet. All right, talk soon. Let's begin. What strategy shall I use? First, we're going to place a point P outside the cycloid. Then I'm going to guess a line's trajectory for a close approximation for T that gets very close to the tangent. Finally, I'm going to use a right triangle to determine alpha using the tangent function. So here we have a cycloid. Let's go ahead and place some grid lines on there so we can kind of get an idea of where in the world our cycloid is. The baseline is x, the arrow going up is y. I have it labeled 1, 2, 3 going up, 1, 2, 3 going from left to right. I have shown pi, and we know that the cycloid is actually 2 pi long and 2 high, and each one would be the radius, so the 2 is the diameter. So let's go ahead and place a point out there, and I'm going to pick a specific value because eventually we have to plug that into our formula. So our point is called 2, 3, 2 on the x, 3 on the y. Now, here's where I'm taking a guess. It's actually a huge guess, and I'm just going to go ahead and put a point T on the x-axis, and we're going to go ahead and draw first the line from point P to point T, and then I'm going to add all the lines geometrically that demonstrate where my angles are. So this is all going to happen at once. Boom, okay? So I have my line PT. I have also shown that the tangent that I'm looking for is crossing the cycloid, but it's making an angle alpha with the horizontal. From geometry, we also know that if I took the radius from point T up, I also have the exact same angle because point PT is perpendicular in quotations for now. We're not exactly sure, but it's very close. Point PT is perpendicular, therefore if I drop a line straight down along the y-axis intersecting at x, I will also have my angle alpha. So from geometry, we know that these angles are identical. So let's continue. I'm going to take t down, and I don't want to deal with t because it's too many variables. I want to deal with x, y, and alpha only. So from a previous video, I demonstrated how to derivate t in terms of pi and alpha. And there they are, pi minus 2 alpha. Now we know that's the distance t along the x-axis. What we also need is our x. Well, we're already given that, thankfully, by our point, 2. So now we have x, we have our t value, and if you look at the bottom leg of that triangle, looks like we have pi minus 2a, and if I subtract x from that, I will have my pi minus 2a minus x. We already know our y value, but I'm going to place y on there just for formula's sake, because again, I'm not using real values quite yet, although we do have constants. We have pi, we have the point p. What we do not have is point t, and that one is absolutely critical. So let me go ahead and put this diagram in the background as we go ahead and explain what's coming up. What I want to do is find angle alpha. So the tangent of alpha is its opposite side over its adjacent side. The opposite side is pi minus 2a minus x. Alpha, of course. Now, guys, these angles are in radians, okay? They're not in degrees. I need radians because I need distance. I need something I can measure around the outside of a circle, and in this case, a cycloid, all over y, which is our adjacent leg. I'm going to manipulate the formula a little bit so that I can find a better way to do the derivation, which eventually is going to have to come, and I'll explain that in a minute. So now we have tan of angle alpha equaling negative 2 over y alpha plus pi minus x over alpha. All I did is rearrange the terms. And now I'm going to set it equal to a function. I'm going to actually turn it into a function, all right? So we have the function of alpha equaling the tan of alpha plus 2 over y alpha minus x, pi minus x over y. And I need to derivate that in order to get into the next step. So let's go ahead and derivate that. We're going to go ahead and derivate the function. And we know that the tan function turns into the secant squared when we derivate, and that's secant squared of alpha plus 2 over y. And you're like, well, what happened to your pi term? Well, they dropped off, okay? They don't contain any terms that were, they essentially turn to 0 because they're all constants. And you'll notice that in the previous screen we had 2y alpha. So again, the constant remains for the alpha variable, but it drops off as well. All right, now into Newton's method. All right, this says that if I take, in this case, x, I'm going to make alpha. All right, and n plus 1 just means the number of iterations or the number of times I'm going to have to run through this formula in order to get the number that I'm approximating, okay? Sometimes you can get exact numbers. In this case, my iterations, I just decided to take it out to whatever, 9 digits, although I'm not using 9 digits in the initial formula. So the first thing to do, if you have angles, convert it to radians, multiply the angle times pi, divide by 180, and that'll give you your radians. That's what I'm using for x. So alpha in radians, or x, equals alpha in radians, okay, minus the entire quantity of the first function over the derivative function. All right, again, if you want information on this, Michael Beeson does an excellent job. And here's the numbers that I came up with. So using x, which was rads, okay, radians, 0.524 is what I started with. I approximated 30 degrees. Obviously, that's a lot slimmer than 30 degrees, but even way off, it worked really well. And after only 4 iterations, alpha became 0.226 radians. Now you need to plug those radians back into your t equals pi minus 2 alpha in order to recover t. Remember, we converted t into pi minus 2 alpha radians because we needed to we needed to get rid of that t value for a while so that we could complete our task. Well, now we want t back. So when we put those approximated radians back into t, that yields us with a t value equals 2.68 on the x-axis. Now plugging t into the parametric equations, again this can be found anywhere online, for the cycloid finally gives us x equals 2.25 and y equals 1.9. So if we go ahead and take a look at our picture, so that gives us our p-value, the blue circle. That's exactly the point where pt intersects the tangent of the cycloid. So again, the base formula for all this is tan of alpha equals pi minus 2 alpha minus x over y. So you're given pi, you know what pi is, 3.14, etc. You're given x and you're given y. The Newtonian method will actually take the tan of alpha and the actual alpha on the other side of the equation and make sure that it becomes equal to itself within the parameters of pi, x, and y. That's the idea here. But this is the base formula. So if you have any point anywhere, plug in all your values and then go ahead and use Newton's method, and it will give you the point along the cycloid where that point and t intersect the perpendicular tangent to that cycloid. Quod erat demonstrandum. All right, that which was shown. All righty. So again, take another look at our lovely diagram, and I'm going to go back through and just finish out the video showing the beauty of structure and all the maths.